Have you ever tried converting an analog signal to digital? How about representing step functions with a continuous counterpart? Do piecewise functions feel like cheating to you? Jean-Baptiste Fourier, our intrepid protagonist, arrived at a solution that can solve all of these problems, but the question he asked was not in that list. Our hero wanted to know how he could solve the heat equation for complicated initial conditions. Forget trains, batteries, and photographs. The math behind heat distribution was the hottest fad in the early 19th century. The heat equation, derived by Fourier himself, describes the change in temperatures across the surface of any metal object over time given an initial condition. In order to understand the heat equation's complexity, we will briefly look at the framework of partial differential equations. First, an ordinary differential equation, or ODE, is a function that describes rate of change rather than a full view of the bigger picture. The variable in which we can describe change in an ODE is typically time. A partial differential equation, however, can relate many different rates of change in a system to each other. The partiality refers to the fact that one variable is only partially responsible for the output because there are numerous other inputs to consider. Take the heat equation, for example. First, we'll clear a few things up. The curly d you see is called del and signifies a partial derivative. It serves the exact same purpose as d does with derivatives, but it is a little special to remind you that one rate of change is only part of the picture. What you see is actually explaining that the change in temperature with respect to time is proportional with the change in temperature of a one-dimensional rod as you travel the x-axis, relying only on the x-coordinates' immediate neighbors. Let's derive this real quick so we can understand it better. Say we take 3 points on our one-dimensional rod, x1, x2, and x3. Each x-coordinate has a corresponding temperature, T1, T2, and T3. Over time, T2 will change depending on its immediate neighbors, T1 and T3. That endpoint can be linked to the average temperature of T1 and T3, T1 plus T3 all over 2. If we subtract T2 from that average and multiply it all by a proportionality constant, we have an expression for the instantaneous change in temperature for x1. Let's equate that to the change in temperature with respect to time. A little algebra later, and we have this equation. However, the t versus x graph contains an infinite number of points. We can change the left side to match our introduction of infinity by turning it into the second derivative of temperature with respect to position. We have arrived at the heat equation. Solving the heat equation for an entire function is hard, to say the least, but Fourier didn't give up after he found the relationship. He wanted his effort to bear some fruit, so he turned to sines. Enter trigonometry. It turns out, when you solve the heat equation for some integer period cosine curve, over time, the function exponentially smooths out. Due to the heat equation's linearity, he found he could add sinusoids to represent more complex functions, and adding the sines' individual solutions actually represented the complete solution to the complex initial condition function's heat distribution over time. So the world of mathematics was gifted a tool to help solve the heat equation for functions that can be represented by sinusoids. But not every function can be equated to an infinite wiggle, right? Wrong. Let's not forget the power of infinite sums or series. As it turns out, pretty much any function can be represented as combinations of simple oscillations. If you have the right series, you will see that adding more and more sine waves together will stop approximating an output that a non-sine function might give you, such as this step function, and start approaching the actual value. It is on this foundation where Fourier's solution to the heat equation lies. Let's take a step back, conceptually, and recall that sine waves can be represented as a point rotating around a circle, or a vector spinning in that circle whose tip is always touching the circumference. If we put our circle in the complex number plane, we can make a sine wave by attaching two vectors with the same magnitude, head to tail, and rotating them in opposite directions with the same frequency. Adding more and more of these vector pairs of differing magnitudes and frequencies will mimic sine summation, as you can see here. In this plane, we can describe the state of each vector with the term e to the it. Just trust me in Euler, I only have 8 minutes to work with. Here are some examples of such vectors and their expressions. Note, the 2 pi refers to the distance in radians of one rotation of the vector. Let's add some more variable control to these expressions, specifically size and direction of the vectors. We will use c sub n as our constant for these values, where n is the frequency. To summarize, since we know that we can represent a complicated function f of t with an infinite sum of sines, and we can equate a sine wave to a rotating vector with the equation c sub n times e to the n times 2 pi times it, then f of t can be equated to an infinite sum of such terms. We are so close to a basic understanding of Fourier series. All that is left to do is understand how we can figure out what c sub n for each term will be. With a careful plan, you will find that all it takes to solve for the constants is simple algebra, and maybe we'll add some integrals for flavor. Intuitively, you can solve for c0 knowing that it will be equal to the average of all the outputs of a sample of evenly spaced values for an input of t. This can be mathematically expressed as c0 equals our initial function with respect to t as we integrate from 0 to 1. How can we solve for the rest of the constants? If we can algebraically equate each term to have n equals 0, then we can use the integral we used before. This can be achieved by multiplying both sides of the Fourier series by c sub negative n times e to the negative n 2 pi it. Now every other term will have completed an integer number of full rotations, except whatever you plug in for n. This allows you to solve for c sub n. In summary, the final equation we arrived at was that our original complicated periodic function f of t equates an infinite sum of our vectors in the complex number plane, each expressed as c sub n times e to the n 2 pi it. This equation is known as exponential form. So there we have it, a simpler solution to the heat equation. Trust me, you don't want to see the other attempts. But the applications of this equation don't end there. In fact, this discovery opened up what can be considered a new branch of math. If you think of sine waves, you may think of the electromagnetic spectrum and signal waves. Well, Fourier series can be applied here in helping transition back and forth between digital and analog signals. This process is used in your computer, cell phones, and many other devices that deal with signals. Economists use Fourier series to understand the stock market and how it may change over time. As physics advances, scientists use these series to understand the universe on the quantum level. In his grueling process of solving the heat equation, Jean Fourier revolutionized the use of sine waves.